Okay, so this is our objective. We're going to solve logarithm equations of log base a of b is equal to k for a, b, or k. So we're going to learn how to solve for all the parts of a log. So when we solve an equation, we have log base 3 of x is equal to negative 3. We're going to rewrite it. So if we rewrite it as an exponential, so now we need to solve for x. Well, then we just do this. So x is equal to 3 to the negative third. We can't have negative exponents, so we make it positive by moving it down to the denominator, and we end up with x is equal to 1 over 27. So then our input for the logarithm must be a positive number, so a, that base, or our answer or solution must be positive. So when we're looking at these two things, let's see, where's my cursor? There it is. All right, so 3 and x have to be positive in this instant. So then if we have log base of 1/3, log base 1/3 of 2x plus 5 is equal to 2, we're going to rewrite it as an exponential. Now this doesn't look too hard to solve. This looks like something we can solve. I know how to find 1/3 squared based on the last unit we just did. So then we end up with 2x plus 5 is equal to 1 over 9. Now there are a couple different ways you can do to solve this. One way is to subtract 5, get a common denominator, and then you'll end up with I think you end up with like negative 44 over 9. You divide by 2, and then you have to find the common, and then you'll have to simplify it. Or you can get rid of that fraction right away. You can multiply both sides by 9 by getting rid of this fraction. So if we multiply both sides by 9, then we end up with 18x plus 45 is equal to 1. Now that's a little bit easier to solve and a lot less steps. Subtract 45 from both sides, and we end up with 18x is equal to negative 44. We divide both sides by 18, and once we divide both sides by 18, we get negative 44 divided by 18, which simplifies or reduces down to negative 22 over 9. So then our solution set is going to be negative 22 over 9. So now let's try this one. Go ahead and get this in your notes and write it, and I want you to write it as an exponential. So you should have gotten x to the 4th is equal to 5. So here's something that we already know how to solve. We learned this in the last unit. We're going to take, how we undo a 4th power is we use a 4th root. So we're going to take the 4th root of both sides. Now we talked about this last unit. A lot of you asked, why is it that we say that the square root of 25 has to be a positive 5? And that's because if we have an even index, it has to equal a positive number, right? We can't take an even index of a negative number, or we don't have a real solution anyway. So when we look at this, we also know that any even power is going to make any number positive. So if any even number is positive, then that's why we have the plus or minus. But here's the extra layer for this unit. We're talking about logs, and this x and this 5 have to be positive, so then our only possible solution is gonna be the 4th root of 5. So while algebraically it is going to be plus or minus of the 4th root of 5, we need to know that those numbers have to be positive, that we have a base, a log base has to be positive, so then that will be our only possible solution. Just something to add an extra layer when we're talking about logarithms. All right, so go ahead and try this one. This one's a little bit more difficult, and we haven't seen anything like that. So go ahead and hit pause and try it. Good. All right, so you should have gotten 36 to the x is equal to the 4th root of 6. So I think what I would do is convert this. I would convert 6, the 4th root of 6, into 6 to the 1/4, so that I have an exponential is equal to an exponential, right? So I don't have two different forms. But then I also can't do anything with that. So what I'm going to do is make 36. So if I end up with, if I make this, I get 36 to the x is equal to 6 to the 1/4. Then I want to make this match this. So I'm going to write this as a base of 6. So what I'm going to do is I know that 36 can be rewritten as 6 squared. And then I can take that all to the x. And I end up with 6 squared to the x is equal to 6 to the 1/4. Now I can use my rules of exponents. I can multiply, and I have 6 to the 2x is equal to 6 to the 1/4, because when you take a power to a power, you multiply. But if I have the same base here and here, then that means that these must be equal to each other, right? There's no way. There's no way that I could have the same base and this be a number without this being equal to this power. So I'm going to set those equal to each other and solve. Divide by 2 and I end up with x is equal to 1 over 8. Now we haven't seen anything like that, and I'm going to talk to you about the property that works with that, but that is really interesting, isn't it? So our solution set is x to the 1/8. So now we're going to define and graph logarithms. So an exponential equation is an equation that has a variable with an exponent such that 9 to the x is equal to 27. So go ahead and get this in your notes, and then get this property for solving exponentials, meaning that for every base a that's greater than 0 but not equal to 1, then if a to the x is equal to a to the y, so any same base raised to, we have different things for powers, then x must equal y. So that's exactly what we just figured out. So I could rewrite 9x to the 27, I could rewrite those as powers of 3, right? So that would be 3 squared to the x, oof, my writing's terrible, is equal to 3 cubed, right? Because 3 cubed is 27. So I can write those as same basis. So that unit that we spent when we found square roots and fourth roots and cubed roots, this is all going to come into play. So go ahead and hit pause and make sure you get this in your notes. Skip it. All right, this is the rules for solving an exponential equation. So make sure you get these steps in. Again, you probably only need to get the bold letters in, but I would get these in. And then we're going to go through an example where I show you each step one at a time. So we kind of already done it, but I'm going to show you again. So go ahead and pause and hit that in. All right, so we're going to solve 25x is equal to 125. So step 1, we're going to write each side with a base of 5. And the reason why we want to do a base of 5 is because I know that I can rewrite 25 as 5 squared, and I can rewrite 125 as 5 cubed. I don't know if I could do 25 because I know that 25 times 3, but that doesn't help me with powers. So we want to be really careful with that. So then we do that, and then we want to simplify our exponents or follow those rules of exponents, and I know that when I take a power to a power, I multiply. So I'm going to end up with 5 to the 2x is equal to 5 cubed. Then I can take my exponents and set my exponents equal to each other. So I get 2x is equal to 3. So then I know that I can solve, so I get x is equal to 3 over 2. Perfect. Then I just need to plug it in. And what's really amazing about this is we actually know how to do this. We know that if x is 3 halves, then what I'm saying here, if I rewrote this, so if I have 25 to the 3 halves is equal to 125, then I know how to rewrite that, right? I'm going to write the square root of 25 cubed. Well, the square root of 25 is 5, and 5 cubed is 125. Boom! That is correct. We figured it out. So I know my slideshow is off. I need to fix that. So this is exactly what we did. And I rewrote it because to me, seeing 25 to the 1/2 is a little bit easier to think about as the square root of 25. Boom. All right, so now we're going to solve exponential equations in the form of a to the x is equal to a to the k for x. I'm sorry. That's the objective that we just did. We worked our way backwards. So now we're going to define a logarithmic function. So if b and x are positive numbers with b not equaling 1, then g of x is equal to log base b of x defines the logarithm function with a base of b. So when we graph them, the first thing we're going to do, so this is where the inverse idea is really going to come into play. This is where it's at. So we're going to rewrite this as an exponential so we can figure out what that is. So if we rewrite it, we get x is equal to 4 to the y. Then we're going to use that to create a table. So when we talked about inverses, where we said if it's an exponential, we switch the x and the y, that's what we're going to do with our table. So when we graphed exponentials, we had -2, -1, 0, 1, and 2. So we could see it at negatives, we could see it at 0, and we could see what's happening at when it's positive. Now we're going to, if a logarithm is an inverse, then we're just going to switch that. So we're going to use those values and plug them in for y to figure out our x values. Kind of like the opposite of what we were doing with exponentials. So here's what we're going to do. We have our y's as -2, -1, 0, 1, 2. We're going to plug that in and figure out what our x is equal to. And when we do that, then we can graph it. So now we have it graphed. We can see the lines. So now we need to think about this. So there's my little tidbit to make sure that when we're doing this that you don't mix them up. So our domain for this, our domain, it's never going to get to an x value that is negative, is it? We'll get really, really small as we go more negative, as the y's become more negative, but it's never going to get to 0. So our domain is going to be 0 to infinity. And our range is going to be negative infinity to infinity, right? See, it's going down forever, and it's going to go up, slowly, but up forever. And then our asymptote is going to be a vertical asymptote instead of a horizontal asymptote, which we just talked about in with exponentials. So we're going to have x is equal to 0, or the y-axis on this one. So if we think about this, this is an inverse. We're switching our x and our y's. Domain and range relates to x and y's, so we're switching our domain and range as well, and that makes sense because we switched the x and the y. So that is something to keep in mind. If you can make that connection, it might help you, especially when we ask you to do this on the test without a calculator. All right, let's try another one. So again, we're going to convert it to an exponential. So we end up with x is equal to 1 over 10 to the y. We're going to make our ordered pair. Again, I didn't do -2 on here because 100 is really big and it would not fit on the graph anyway. We're going to graph it. We're going to see that line. And again, our domain and range is the same. Our domain is negative infinity. Our domain is going to be 0 to infinity because it stays positive right here. Let's see if I can point it out. Right here. And then we have that it's never going to cross that y-axis. We have our range, which is going to be negative infinity to infinity, and then we have our equation of the asymptote, which is going to be x is equal to 0. And think about that. When it was an equation of the asymptote for the exponential, it was y equals, and what do? We switch the x and the y. All right, so these are the rules. Again, you don't really need to write number 1. 2 saying that a is greater than 1, the graph is going to rise from left to right. When a is not negative, but a fraction or a decimal, so less than 1, then it will fall from left to right. And then I would make sure that we have 3 and 4 written in your notes, if I get that out of the way. So make sure you have that, because that is like the other side of what we did for exponential. All right, that is the last thing I covered today in class. I hope you have a great day, and I'll see you all tomorrow.